Okay, I'm going to show you how to get through the rider problem to merit level. So we have a fairly small amount of context with this problem. Rider problem, a company produces boards in two types, rider and performa. So we're going to just we only have two variables here that we have to worry about, and we have to make sure that we identify what those two variables are somewhere in the assessment. So we're going to make X our number of rider boards and Y our number of performa boards. Because if you read the rest of the context, they basically want to figure out how we can maximize our profit for rider and performa boards. So we do that, and then what else we have to do is we have to write constraints. We have to identify what all the constraints are that the person is working under, and so that they can maximize or minimize something. So in this case, it's a maximizing profit. Sometimes it's minimizing something. So we'll read this. Under existing contracts, they must build at least 40 rider boards and at least 60 performa boards. Now, just because they're in the same sentence doesn't mean it's all one inequality. This is X and this is Y. So at least means we have to make 40 or more boards. At least 60 means we have to make at least 60, so 60 or more boards. So when we write the constraints, we write them as X is greater than or equal to 40, Y is greater than or equal to 60, because they have to be 40 or bigger, 60 or bigger for rider and performa boards. So those are two constraints there. And another constraint is the limit of production. They can only make a total of 200 boards per month. That's the maximum production that they have for that facility. So that's X plus Y as a total is less than or equal to 200. So can't make more than 200 boards. They don't have the capacity for that. And the last constraint is the materials. So it costs $60 materials for the rider board and $80 for the performa board materials, and they have a budget of $14,400. So they can't exceed that. So that's 60X plus 80Y as the material costs, and then they can't exceed the 14,400. So less than or equal to 14,400. So those are our four constraints in this situation. So the next thing that you have to do is graph these, right? So remember that when we graph this with Desmos, when we put this into Desmos, we have to flip the signs because Desmos doesn't shade away. And so in order to get this to shade away, we're going to put in, flip the sign, X is less than or equal to 40. And then Y is going to be less than or equal to 60. And X plus Y. And we got to flip the sign, so that's greater than or equal to 200. And then 60X plus 80Y is less than or equal to, so we got to flip the sign, 14, 40, oh, 14, 400. So we end up creating, by shading away, this white area in here, unshaded area. This is our feasible region. Now, within that feasible region, we're going to have a number of points of intersection between the lines that we've drawn in here. And in this case, we have 1, 2, 3, 4 points of intersection within the feasible region, and these are them. So you need to make sure that you write these down. So, and we'll have to record the graph and write down these points of intersection. And excuse me, once we've done that, then we go hunting back into the problem for something called the objective function. Now, the objective function is a function that is not a constraint, and what it does is helps us to optimize the situation that we have. So you go hunting for another set of information, and it's excuse me, right here, that has to do with either maximizing or minimizing something. They'll say that in the sentence. So if a profit of $40 per rider board and $50 per performa board is made, find the maximum profit that can be made per month. So that's our objective function. So we write it as an objective function. Profit, the maximum profit we're trying to find is equal to 40x plus 50y, because 40 is what they're going to make on profit for the rider boards, and $50 is what they're going to make on the performer boards. And then what we do is we take our points of intersection. Now make sure you write these down somewhere. So A, B, C, D, the points of intersection in the feasible region are these, right? 40 and 150. Now make sure you understand what this means. This is 40 rider boards and 150 performer boards. This is 80 rider boards and 120 performer boards, and so on. And what we do with those points of intersection is we put them into our objective function. So 40 times x, which is 40 times 40, plus 50 times y, which is 50 times 150, and we figure out what the profit is when we put that point of intersection in. And we do the same for 8120, and we get 9,200, and we do it for 4060, and we do it for 140 and 60. And we see that we get a maximum profit right here, the 9,200. And what that tells us at merit level is that that combination of 8120 is, with the constraints built in, that's the maximum that they're going to be able to make in profit, and so that's what we're looking for. So to answer the question, a couple of sentences. Therefore, the maximum profit cost, 9,200, the company can make per month from the combination of rider and performer boards is at point 80 and 120. And then just put it in context, the maximum profit is 9,200, which the company can get per month by selling 80 rider boards and 120 performer boards to merit. That's it.